Today's lecture will be about floating point. So this is the outline of my presentation. I will be talking about floating point numbers, the IEEE 754 standard, talk about how we do comparison, addition, subtraction, multiplication in floating point. So floating point arithmetic. And I will conclude with the MIPS floating point instructions and some examples how to write programs using these instructions. So first, we have seen integers so far. We understand integers, how we can represent signed integers in the 2's complement representation. So we can represent positive and negative numbers. But the word is not just integers. We also have floating point numbers. So these are used in programming languages. We have the type float, we have the type double in high-level programming languages, and these mean floating point numbers. For example, these numbers that have a fraction like pi, like e, we can use the scientific notation. For example, when we use here, let us say 1.0 times 10 to the power negative 9. Okay, if you look at this number here. Okay, so this number is very small, tiny, okay, very close to 0. So even though the exponent is negative, the number itself is positive. So this is how many seconds you have in a nanosecond. You can also calculate the number of nanoseconds in a day. This will be a very large number. It will be this one. So notice that we are using the scientific notation, and we can use it to represent very small numbers, numbers which are very close to 0. And we can use it to represent very large numbers. So we call this the scientific notation. And you can start with a plus or minus. This will indicate the sign of the number. There is one digit before the decimal point, followed by a fraction. And then we multiply this by 10 to the power an exponent. The exponent itself can be positive or negative, and this has nothing to do with the sign of the number. So these are some examples of floating point numbers in base 10. The first number is negative. So notice that there must be a single digit before the decimal point, and this digit must be from 1 to 9. So the number must be normalized. This is the meaning of normalizing the number. That's the standard way of writing the number, a floating point number. And then you have a fraction here after the decimal point. And then you have 10 to the power the exponent. This is the exponent here. That's another number here. You can see that the exponent is -1. Okay, this is the exponent. Now these numbers are in base 10. Notice that we have here 10 to the power, 10 to the power 3. We have 10 to the power -1. So the base is 10. So these are decimal floating point numbers. We can have binary floating point numbers in base 2, but here you have to use only 2 digits, 0 and 1. So notice that here we have, this is what we call the binary point. This point here is called the binary point. Now there must be exactly 1 bit before the binary point, and this bit cannot be 0, it must be a 1. So here is a number, okay, and you can see the exponent is 23 and the base is 2. So it's multiplied by 2 to the power 23. So minus 1.00101. Notice that the fraction itself is in binary. So this is a binary floating point number. So the base is 2. I'm showing the exponent in decimal just for clarity. So here times 2 to the power 23. So notice that the base here is 2. Same thing here. The base is 2. The exponent is -3. And this is the number. Okay, 1.101101. This is all in binary. Okay, this is in binary. And you can see the base here is 2. And the exponent is -3. So we keep the exponents in decimal for clarity. Okay, so notice that here the decimal is 23, here it's -3 for clarity. But of course, we are going to store the exponent inside the number. When we store it inside the computer system, we are going to store the exponent itself in binary. I will show you the details about the exponent in a minute. But for clarity, I'm showing the exponent in decimal in these numbers. Now, floating point numbers should be normalized. And the meaning of normalizing a floating point number is that there must be exactly one non-zero digit. It should appear before the point. In the case of decimal, you can actually have the digit from 1 to 9. It cannot be 0, so it has to be from 1 to 9. In the case of binary, there are only 2 digits, 0 and 1, so it cannot be 0, so it must be 1 in the case of binary. So it is always 1 dot, and then we have the fraction. So these are examples of, this is normalized. You can see it's in decimal. This is also normalized, but it is in binary. You can see that the base here is 2. Whereas these two numbers here are not normalized. Now the first one, you can see there is a 0 before the decimal point. Here you have multiple bits before the binary point. So the second number is in binary. You can see it's 2 to the power -6. So it is in binary. It's ones and zeros. And there are multiple bits before the binary point. So for this reason, it's not normalized. Now you can take any number which is not normalized and you can force it to be normalized. You can normalize any floating point number. Now in the case when you have leading zeros, so what you have to do is that you have to move the dot here after the first non-zero digit. So it has to appear after the 5. So it is as if you are shifting the digits to the left. So when you shift the digits to the left, you have to decrement the exponent. So these two numbers, okay, so these two numbers are equal. Yani for example, you can always take this number here, okay, which is -0.05341, and you can shift, okay, the digits here to the left so that this 5 here appears before the decimal point and it becomes this number here, up. So if you normalize it, you have to change the exponent. So you have to decrement the exponent. So now since we are shifting the digits 2 places to the left, we have to decrement the exponent by 2. Okay, because this number has leading zeros. So it starts here with 0.0, okay? So we have 2 leading zeros, so therefore if you would like to normalize it, it becomes normalized as shown up, and you have to decrement the exponent by 2. So these two numbers are equal. Now in the second case, if you look at this one, you have 4 bits, okay, that appear before the binary point. So what you have to do is that you have to shift these bits to the right. So we need to shift these 3 bits to the right, these 3. So when you shift them, they will appear here after the binary point as shown up. This is how we normalize. But then you have to add, you have to increment the exponent because we are shifting to the right. So we have to add +3. So we have to add, in the case when we are shifting the bits to the right, this is how we normalize. So these two numbers are also equal. So this is what we get after we normalize the number. So these two numbers are also identical. They are the same, but the one which is on top is normalized and the one at the bottom is not normalized. So we can take any number which is not normalized and we can normalize it. Okay, is this clear? Do you have any question about this?
Clear.
Yeah, تفضل. Yes.
Is the base of 2, I mean, why it's necessary to be 1?
So in the case of decimal, we use the base 10, as shown here, 10 to the power, and then we have an exponent. In the case of binary, the base must be 2. So it's 2 to the power 23 and 2 to the power -3 and so on. So therefore, it is 2 to the power an exponent. So we use the base 2 in the case of binary floating point numbers, and we use the base 10 in the case of decimal floating point numbers. So we are used to the decimal floating point, but inside computer systems, we use binary floating point. Okay? So the base must be 2 in the case of binary floating point numbers. Now, in the case of bits, when you shift the bits here, notice that when you shift to the left or to the right, this is like, when you shift to the right, this is actually division by 2. When you shift to the left, this is like multiplication by 2. We have seen these in the case of integers, right? So in the case of an integer, when you take an integer binary number, okay, and you shift it to the left, this is multiplication by 2, right? And if you shift the 2 bits to the left, this will be multiplied by 2 to the power 2 and so on. So you count how many bits that you are lifting it, you are shifting it to the left. And this is multiplication by 2 to the power a certain exponent. If you are shifting to the right, this will be division by 2 in the case of an integer. Remember that when we talk about shift left and shift right and how we can use this, okay, to multiply by a power of 2. The same thing. So this is for this reason, in the case of binary floating point, we use the base here equal to 2. You can see the base is equal to 2. Okay, so we don't really want to change the value of this number. So when I shift to the right, I'm really dividing. But in order to counter this division, because we don't really want to divide, we have to multiply also by 2 to the power 3. So therefore, we adjust the exponent. We adjust the exponent so that these two numbers will be equal, will be identical. Okay, they will have equal value. But if the one which is on top is normalized, whereas the one which is at the bottom is not normalized. Okay, is this clear? So this is the meaning. So this is the meaning of normalized floating point numbers. I can give you, for example, another example. I need to use my pen tool. Okay, just 1 second. Give me 1 second. So you can take any number, okay, which is not normalized, and you can normalize it. Okay, for example, I have, let us say, this number here in binary. Okay, so for example, suppose I have the number 0.0000. Before you encounter the first one, and then you have here, for example, let's say 0.11101. Okay, times 2 to the power. It has to be base 2 because this is a binary number. Okay, so suppose that this is, let us say, 2 to the power 10. Okay, and I would like to normalize it. Notice that the point appears here. So what will be this number after normalizing it? If I would like to normalize this number, what do I get? So this is not normalized because we have leading zeros, right? So notice that we have a 0 before the binary point. So this is not normalized. So let us normalize this number. I have to move this. I have to move this one here. Okay, to make it appear, okay, before the binary point. So we have to count that how many bits we need to shift to the left. So let us count these. So we have 1, 2, 3, 4, 5. Correct?
Yes.
So what we have to do is that we have to rewrite it like this: 1.011101. But what will happen to the exponent? It's 2 to the power what?
5.
Yes. So we have to decrement the exponent by 5 because we shifted all the number here. Okay, so we had 5 leading zeros. So for this reason, we have to decrement the exponent. So whenever you have leading zeros, you decrement the exponent. But when you have multiple bits appearing, okay, to the left of the binary point, you increment the exponent. So this is the rule. Okay. So this is the rule that we use when we are dealing with floating point numbers. Any question about this? Is this clear?
Yes.
Now I need to talk about more details about floating point numbers. Okay, When you would like to represent a floating point number, there is a representation for it, okay, which is used in computer systems, and there is a standard. So we are going to represent the floating point numbers by three fields. We have the sign field. Okay, it seems that there is a bad network quality. Okay, so let's just, okay, it seems to be okay, fine. So we have a sign bit, okay. We have an exponent field and there is a fraction. So these are the, so we have to represent a floating point number by these three fields. S is the sign, okay. And we have E here is the exponent, and we have F is the fraction. So we have the exponent field and we have the fraction field. So these are the three things. Now the sign is just a single bit. So we use 0 for positive and 1 for negative. This will indicate the sign of the number. And we have sign magnitude representation. So we are separating the sign from the magnitude. The magnitude is represented by the exponent field and the fraction field. So the exponent field itself is represented in binary. This will indicate the exponent of the number. Remember that the base is 2 because this is a binary floating point number. And we have a fraction field. So this will indicate the bits that appear after the binary point. Now, if you have more exponents, if the exponent field is large, you can represent a wider range of exponents and therefore a wider range of values. So if you have more bits in the exponent field, this will increase the range of values. If you have more bits in the fraction field, this is going to, improve the precision. Okay, we can increase the precision of the floating point number by adding more bits to the fraction. So more bits in the fraction is like you have more significant bits, or if we convert it to decimal, you will have more significant digits in the floating point number, and this is going to improve the precision of the floating point number. So the precision is defined according to the number of fraction bits. Okay, that's the meaning of precision. So now the IEEE standard, okay, is defined. Why? Because they want to standardize the representation of floating point numbers across all computers. Before the 1980s, different computer manufacturers, they have slightly different representations for floating point numbers, and there was no standard. And this made it very difficult, okay, if you have, let us say, applications that you would like to port from one computer system to another computer system to produce exactly the same results. Okay, so the results differ because the floating point has a different representation. So in order to standardize the representation of floating point number and to simplify the porting of floating point numbers and to unify the development of floating point algorithms, there was a need for a standard. So the standard was introduced in the 1980s. And the standard defines more than one precision. Okay, so they define single precision floating point numbers. So these single precision floating point numbers occupy 32 bits in memory. So each number will be 32 bits. And this is the type float, which is used, for example, in C and in Java and many high-level programming languages. We have the type float. So it means single precision floating point numbers. So there is 1 bit for the sign. There is always 1 bit for the sign. We have 8 bits for the exponent, and we have 23 bits for the fraction. So that's the standard way, okay, to represent a single precision floating point number. Yes, Mushtaba.
Doctor, can you go back to 202 and talk about the sign and magnitude representation?
You see that in the case of the 202, we never talk about the floating point numbers. We talk about integers. Now, in the case of integers, we represent them using the 2's complement representation. This is the standard way to represent signed integers. So we use the 2's complement representation. But floating point numbers, we did not talk about it in the 202 course. Do you remember anything about?
I mean sign and magnitude representation.
Well, sign magnitude is not used for integers. It is used for floating point numbers. So remember that for integers, we never use sign magnitude. We use the 2's complement representation. This is the standard way of representing signed integers inside computer systems. So today, all computer systems, they use the 2's complement representation to represent signed integers. But for floating point numbers, it is the sign magnitude, because in the case of floating point number, the sign is separated from the magnitude of the floating point number. And the magnitude, it has an exponent part. You don't really see an exponent part in the case of integers. There is no exponent.
Mm-hmm.
Correct? Okay.
Correct.
So that's in the case of floating point numbers. So it is sign magnitude, and the magnitude has an exponent and a fraction. Now, to standardize this, there is an IEEE 754 standard. Okay, that's the name or the number for the standard. In the case of single precision, it's 1 bit for the sign, 8 bits for the exponent, and 23 bits for the fraction. In the case of double precision, we also have 1 bit for the sign, but the exponent field is larger. It's 11 bits. So it's an 11-bit exponent field, and the fraction is even much longer. It's 52 bits for the fraction. So the number occupies 64 bits in memory, each double precision. So we call it double because it's using double the number of bits. Okay, and it's improving the precision by using a longer fraction, 52 bits for the fraction, rather than only 23 bits for the fraction in the case of single precision. So that's why some people prefer double precision over single precision, because it has a longer fraction, and therefore more significant digits can be represented with double precision. Okay. So it depends, of course, on depending on the application. For example, in scientific computing, people prefer double precision because they can have more significant digits. Yes, Khalid. Khalid?
Yes, Doctor, can you hear me?
I can see your hand.
Can you hear me?
Of course, yes.
I wanted to ask about the sign of the exponent.
Okay, I will go into these details in a minute. I'm coming back to it. So the S here is the sign bit of the number, but the exponent itself can be positive or negative, and we have a special representation for the exponent itself. Just bear with me, okay? In a few minutes, I will be talking about the exponent field, okay? Fine. So that's the IEEE 754 standard, okay? So there is another thing about this standard, is that all the floating point numbers must be normalized. So a normalized floating point number, okay, well, let me be more accurate, okay? So the standard way of representing a floating point number is normalization. To have a unique way to represent a floating point number, then the floating point numbers must be normalized. So a normalized floating point number consists again of 3 fields. S is the sign, E is the exponent, and F is the fraction. Now, because the significant here, okay, because the number is normalized, there is always a 1 and a dot before the fraction field. So we call this the significant. So the significant here is defined as 1.f, and F is the fraction. And F consists of all of these fraction bits, F1, F2, and so on. Okay, depending, of course, on how many fraction bits we have. If we have single precision, we'll have 23 fraction bits. If we have double precision, we'll have 52 fraction bits. So all of these fraction bits appear after the binary point, and there is a 1 and a dot. Now, the 1 and the dot here are hidden. They are not stored inside the number itself. So we assume the existence of a 1 and a dot before the fraction because the number is normalized. And we say that the significand is 1 bit longer, okay, than the fraction. So the 1 and the dot are not stored in binary inside, okay, the normalized floating point number. They are assumed to exist, okay, so they are implicit. They are not explicitly stored, and therefore the significand is always 1 bit longer. So if the fraction is 23 bits, the significand is 24 bits. If the fraction is 52 bits, in the case of double precision, then the significand is 53 bits. So you can see it's 1 bit longer than the fraction. Now you can see what's the value of a normalized floating point number. Now, since there is always a 1, and because the number is normalized, and therefore there must be a digit before the binary point, and this digit must be a 1. So therefore, the value of a normalized floating point number is 1 dot the fraction multiplied by the exponent value. I will talk about the exponent value in a minute, but what's the value of the significand? The value of the significand is 1 dot f1, f2, etc. times 2 to the power the exponent value. Notice that the base is always 2. We assume it to be 2 because the number is in binary. Okay, it's a binary floating point number. So you don't really see the 1, the dot. These are not really stored. Okay, they are assumed to exist. Also, the 2 itself, the base, it does not exist inside the number. It's assumed to exist. Okay, times 2 to the power the exponent value. So if you would like to expand this, it will be plus or minus according to the S field, the sign bit here. And then you have 1 plus fraction f1. That's the first fraction bit that appears here. If I would like to use my pen tool, so f1 will be here. Okay, that will be f1. Then f2 will be the next bit. Then f3 and so on. So all of these are the fraction bits. So we multiply f1 by 2 to the power negative 1. We multiply f2 by 2 to the power negative 2. So these have negative exponents because these are fraction bits. So if f1 is equal to 1, it means that its value is half. If the value of f2 is 1, it means that its weight here is 1 over 4. It means it is a quarter. And then we have, if f3 is equal to 1, we multiply it by 2 to the power negative 3. It means 1 over 8. Then we have 1 over 16 and so on. So these are the weights of the fraction bits in the fraction field. Now, all of this has to be multiplied by 2 to the power the exponent field. Okay. And again, the exponent can be positive or it can be negative because the exponent itself is signed. Okay. Is this clear? That's basically the value of a normalized floating point number. What about the exponent? This now comes back to your question, Khalid, because you asked about the exponent. How do we represent a signed exponent inside the exponent field? So the exponent inside the exponent field must be signed. There are choices here. We can use a sign and magnitude representation for the exponent. Yani inside this exponent field, I can introduce a sign bit here, okay, for the exponent inside the exponent field. That's one choice. A second choice is to use the 2's complement representation. Why? Because the exponent itself is nothing but an integer, right? That's an exponent. The exponent itself is nothing but a signed integer, and therefore we can use the 2's complement representation to represent the exponent. And the third choice is the biased, okay, representation. Now, the IEEE standard did not choose sign magnitude, did not choose the 2's complement representation. They used the biased exponent to represent the biased representation to represent the sign exponent. So the exponent is biased. So what is the meaning of biased representation for the exponent? So they define the exponent value as E minus a bias. The bias is just a constant. I will tell you how the bias is defined in a minute. Okay, so So here, okay, when you look at the exponent value, when I say here exponent value, 2 to the power of the exponent value. Now this exponent value, which is shown here in this slide, is nothing but e, which is the way that we are representing the exponent in binary, minus the bias. So e itself is always unsigned. So if we use for example, single precision, the exponent field is only 8 bits. If you look at the exponent field e, it has a range from 0 to 255 because it's represented in binary, okay, using 8 bits. So that's actually the e, the exponent field. But that's not the value of the exponent, okay? That will be unsigned. But I really would like to find the signed value of this exponent. So to calculate the signed value, we are going to define a bias. So how do we define the bias? Now, they said in the standard that we are going to reserve e equal to 0 and e equal to 255. These two values are reserved for special use. I'll come back to these two values later, okay? So e equal to 0 and 255 are not used to represent normalized floating point numbers, okay? They are used for something else, okay? So we are left with the range from 1 to 254. So we have 254 possible values for a normalized floating point number. So you look at the exponent. If the exponent is from 1 to 254, it means that the number is normalized. So they said, okay, what is half 254? It's 127. That's it. So they defined the bias to be equal to 127. So now they said, okay, the exponent value is e minus the bias. So what is the bias? The bias is 127 for single precision. So this is how they define the exponent value. But the range of e is from 1 to 254. So replace e with 1. So 1 minus 200. So 1 minus 127 is negative 126. And when e is equal to 254, 254 minus 127 becomes plus 127. So therefore, 1 becomes negative 126, and 254 becomes plus 127. So we store e, okay, from 1 to 257, but its value is from negative 126 to plus 127. So this is why we say biased representation. In other words, that the exponent field E is in excess to 127 because the bias is defined to be 127. That's how it is defined. This is the meaning of biased representation. Now, that's for single precision. Let us repeat the same thing for double precision. So for double precision, we have 11 bits for the exponent field. So the exponent field is longer, it's 11 bits. And if you store a number here, okay, an unsigned integer using 11 bits, you can go from 0 to 2047, which is 2 to the power 11 minus 1. Okay, that's 2047. So we have this range, but this is for the biased exponent. That's actually for the exponent field. Okay, that's E. Now, again, there are two extreme values, two extreme cases, E equal to 0 and E is equal to 2047. So these two values, okay, are not used to represent normalized floating point numbers. They are reserved for special use. Okay, so let me just say reserved here for special use. The rest from 1 to 2046, these are for normalized floating point numbers. If we divide 2046 by half, you get the bias, which is 1023. And we say that the exponent value is E minus, 1023, because the exponent is always 1023 in the case of double precision. So remember, in the case of single precision, the bias is 127. And in the case of double precision, the bias is 1023. These are how they are defined for single precision and for double precision. So now when the exponent field is 1. 1 minus 1023 is negative 1022. And when you go to the maximum here value, 2046 minus 1023, it will give you plus 1023. So this is the range. Okay, so this is the range of exponent values that we can represent from negative 1022 to plus 1023. So again, what's the value of a normalized floating point number? We can write it now 2 to the power the exponent value, but the exponent value is e minus the bias. So look at the e, the exponent field, and minus the bias, okay? And this is the significant here. So all of this is the significant, and it must be multiplied by 2 to the power the exponent value. So the exponent value here is e minus the bias, okay? And because you are subtracting the bias, this is why we call it, okay, biased exponent, okay? Or this is the biased representation for the exponent. Do you have any question about this? Is this clear? Questions? Did I answer all the questions? I have some,
no.
yeah, okay. I do have some examples about this to clarify this. I do have some examples. Let us take a look at this number here. Now, this is number which consists of 32 bits. Here, if you'd like to count them, these are 32 bits. I have 1 bit for this sign. So that's my sign bit here, which is shown in green. And I have 8 bits for the exponent, and I have 23 bits for the fraction. So clearly, this is singular precision float. And I'm showing the 3 fields here, okay, in different colors. Okay, so the most significant bit is the sign, and then followed by the exponent, and followed by the fraction in exactly this order. This is how the number is represented in binary. Okay, in total, we have 32 bits. Now, if you look at the sign is positive or negative?
Negative.
Is this number negative? Clearly, it's 1. It means it's the negative number. Okay. Now, how about the exponent? Now, that's actually e. That's my biased exponent. That actually is e. I'm just writing with my mouse, and this is my fraction f. Okay. So my exponent e here consists of 8 bits, but this actually is my biased exponent. So you have to subtract the bias, which is 127. So you have to say, okay, what is the value of this exponent field minus the 127? This will give you the exponent value. So if you look at this number here, converted from binary to decimal, you get 124. But you'd say 124 minus 123, you get negative 3. So the exponent, the exponent field E here is 124, but the exponent value is negative 3. So it is stored as 124, but its value is negative 3. So this is how, okay, we represent negative 3 in binary. We represent it as 124. This is the meaning of the biased exponent. So it means that the way that we are storing the exponent field, it's always in excess to the bias, which is 127. In other words, if the value is negative 3, add to it plus 127, you get 124, and store the exponent field as 124. Right. So that's for the exponent value. Okay, the significant is 1 bit longer. Remember that the 1 and the dot, they are implicit. Now we know that they are implicit because the number is normalized. Okay, so it's a normalized floating point number. So it's 1 dot the fraction. So this is my fraction here. This is the fraction field. The 1 and the dot, they do not appear in the fraction field. They are implicit. So it's 1 plus, then this is 0. This is 2 to the power negative 2. That's 0.25 in decimal. Okay. So now the significant is just 1.25. The 1 and the dot themselves are implicit. So now we say that what's the decimal value? What we have to do is I just have to clean up here what I wrote. Okay. Okay, so it's negative 1.25 times 2 to the power negative 3, you get this number, okay, minus 0.15625. So I just obtained the decimal value of this binary floating point number. So given the number in binary, you can always obtain its decimal value. Is this clear? That's a solution, okay, for this example. Okay, let us do more examples. Okay, what about this one?
This is positive.
It is a positive number. Now, notice that here I said negative because the sign was negative. Here it is positive. Now, notice that this is 128 plus 2, it's actually 130. But that's the biased exponent. The exponent value is what? The exponent value is what? So we have to multiply the significant by what? 2 to the power what? 130 minus 127 will give me what?
130.
3.
No, this is actually is 130. If you look at the decimal value of this, okay, that's my biased exponent. It's 130. So this is E is equal to 130. But what's the decimal value? So what is the exponent value? Sorry, what's the exponent value? It's 130 minus the bias. So 130 minus the 127 will give me just 3. So the solution is that we have to write one dot followed by all of this fraction. This is all my fraction here, right? So we write the fraction here. The 1 and the dot are implicit. They are not really stored as part of the number. And 2 to the power 130 minus the 127. So if you extend it, you get 2 to the power 3. So you have to multiply this number by 2 to the power 3. So when you multiply by 2 to the power 3, you have to move the dot 3 places, 3 bits to the right. So it becomes 10 point. Here we have 0, 1, 1. This will be 1 over 4. This will be 1 over 8. It will be 0.375. So this number is 10.375. That's how you represent 10.375 as a floating point number, as a single precision floating point number. I have more examples about double precision, okay, floating point numbers. Let us take a look. The bias is different. Okay, so remember that the exponent field is 11 bits and the fraction field is 52 bits, and there is always 1 bit for this sign. So in the case the exponent, the value of the exponent, you look at the biased exponent. This is E. That's actually is E minus the bias. So it's 1029 minus 1023. The bias is 1023. Okay, for double precision. So you have to remember the bias for the single precision and the bias for double precision. So for single precision, it's 127, and for double precision is 1023. So this is the bias. If you subtract, you get 6. Okay. So now, if you look at the decimal value, you have to take 1 dot the fraction, but you have 52 bits of fraction here. Notice that most of them are zeros. Okay, I'm just keeping the example simple, but you can actually have many ones in the fraction. And then you have to multiply it by 2 to the power 6. So when you convert, okay, to decimal, so you multiply by 2 to the power 6, you can move the dot 6, place 6 bits to the right. You place it here. Okay, you count 6 bits, and you place the dot here when you are multiplying by 2 to the power 6, because this actually is a positive exponent value. So you get 74.5. This is actually half, and the remaining fraction bits are all zeros. Okay, so that's the decimal value. Let us do 4 more. You can actually try it yourself, and you should actually get this number. Okay, so if you look here at the exponent value, it's -7. We got a negative exponent value, -7. Okay, which is the E minus the bias. So this E minus the 1023 will give you -7. So the exponent value can be positive or negative. Notice that the sign is also negative. So the number itself is negative. Okay, that's the sign bit. So this is the final decimal value. Right, is this clear? So these are examples of double precision floating point numbers. Okay, you might ask, okay, how do I convert from decimal to binary? How do we do it the other way around? So suppose that now my decimal number is this, and I would like to represent it as single precision or double precision. What shall I do? What shall I do?
Normalize first.
No need to normalize in decimal. You need to normalize in binary.
Multiply by 2 and take the...
Convert this actually to binary. Convert it to binary. That's this is what you should do. So convert it to binary, you multiply by 2, and you look actually what you get as. So with the fraction, because this is just completely fraction, just we can just have multiplication by 2. So when you multiply by 2, you get the fraction bits. So you get 1.625. So the 1 here is my first fraction bit. You take the fraction, which is 0.625, and multiply by 2, you get 1.25. So you get another one. That's also my second fraction bit. So multiply 0.25 by 2, you get 0.5. So 0 must be my third fraction bit. 0.5 times 2, you get 1.0. So 1 is my fourth fraction bit. Now you have the fraction here equal to 0. So stop when the fractional part is 0. Because if you continue, you will just get zeros. So 0.0 times 2 is 0.0. 0.0 times 2 is 0.0. So we stop, okay, when the fractional part is 0. Let me switch here to my highlighter. So this is when you stop, when the fractional part is 0. Okay, or if you don't really reach 0, you continue like this until you have sufficient fraction bits. So we have a limited number of fraction bits that you can store. We have only 23 fraction bits in the case of single precision. So if you have obtained all the required fraction bits, you stop. Okay, because you cannot store more fraction bits. And notice that now in binary, 0.8125 is 0.1101. Now you can imagine you have infinite number of zeros, okay, to the right after the least significant one. Okay, so these remaining fraction bits are all zeros. Okay, now if you would like, you can convert the fraction back from binary to decimal. So this would be 1 over 2 plus 1 over 4 plus 1 over 16. This will give me 13 over 16. And 13 over 16 is 0.8125. You can verify that your conversion of the fraction was done properly. Right, so now we have, this is the binary fraction, 0.1101. What is next? What should we do next?
Normalize.
Normalize. Now we need to normalize. There is 0 dot. It's not normalized. So what I have to do is that we have to normalize it. So to normalize, we have to move the place of the dot as if we are shifting the bits to the left. And because we are shifting, we have leading 0 here. We have to decrement the exponent. So it's just 1 bit, okay, to the left. So therefore, we get 1.101 times 2 to the power negative 1. Notice that the exponent is negative. Why? Because we have leading zeros. That's why. Right. So now it's normalized. What is next? What is next? Now, this negative 1 is the value of the exponent. But the representation of the exponent must be biased. So what we have to do is that we have to represent this in binary. You have to tell me what's the binary representation. Well, we're not going to store the 1 and the dot because these are implicit. We're going to store the fraction. So the fraction starts with 101 followed by all zeros. The biased exponent will be -1 plus the bias, which is 127 for single precision, or we have 1023 for double precision. Okay, so what you have to do is that you have to practice doing this. That's it. You have to practice. And therefore, if you add the bias, you get 126 for single precision, you get 1022 for double precision. Okay, that's actually is the exponent value, but you have to add the bias to make it a biased representation. So notice that for single precision, 1 is the sign of the number because the number is negative here. It says minus. So we have to put 1. This is 126 in binary. That's my biased exponent field. And this is the 101. Okay, that's actually the 101. Let me use my pen tool. So this is my 101. This is my fraction. It appears here. All the remaining fraction bits are all zeros. Okay. If you would like to do it for double precision, no problem. This is 1022. That's the exponent field. This is again the 101, and all the remaining fraction bits are all zeros. Sometimes we get actually more ones. This is a simple example. Now, let me ask you this question. What is the largest normalized float we can have? And if I would like to have the largest normalized float, okay, what will be its binary representation? It will have to have the largest exponent value, and also it will have to have the largest fraction. So if I would like to answer my question, this will be the solution for singular precision. Okay, so notice that the largest exponent value, it cannot be all ones, because all ones, this will be 255. It is reserved for special use. So it has to be 254. That's the largest exponent for a normalized floating point number. And the largest fraction will be all ones. So now we'll say what's the decimal value? So 254 minus 127. Remember that the exponent is biased. So we have to subtract, okay? We have to subtract 127 from the exponent, okay, to get the value. So the value here is plus 127. This is the largest exponent for single precision. And the significant will be 1 bit longer than the fraction. So it's going to be 1 point followed by many ones. Now, if you convert this number from binary to decimal, so we have here 23 ones in the fraction, you will get 1 point, okay, many nines. In fact, you will get 6 nines after the decimal point, followed by 8 if you convert this number from binary to decimal. Now, that's not 2. This is almost equal to 2. Okay, it's very close to 2, but it's not exactly equal to 2. Okay, so this number is very close to 2, but is slightly less than 2. Okay, so that's the number in decimal. Now, if you say, okay, what's the value of this floating point number? It will be approximately 2 times 2 to the power 127, which is 202 to the power 128, which is this number in decimal. It's a large number, and this number is the largest that can be presented using single precision. Notice that it is times 10 to the power 38. So the floating point representation allows you to use large exponents and allows you to represent very large decimal values. So that's the value in decimal. This is the largest normalized float. Now you might repeat this for double precision. Now for double precision, we have a lot bigger exponent. So the exponent, this will be the solution for double precision. Now this number here consists, or this exponent consists of 11 bits. So if you look at its value, okay, remember that it cannot be all ones, because all ones is reserved for a special use. I'll come back to it in a minute. So this will be 2046, and we have followed by a fraction which is all ones. We have 52 fraction bits which are all ones. So the value in decimal, it's 2 times 10 to the power 1023. So this 1023 is the 2046 minus the bias, which is 1023. You get 1023, which is approximately 2 to the power 1024. And can see here we have 10 to the power 308. So it's like having 1 and 308 zeros. Okay, so this is really a huge number, a very large integer value, and this shows the largest floating point number that can be represented. Okay. Now, what happens if we have a number which is larger than the maximum normalized floating point number that can be represented? What if we have a number which cannot be represented, larger than the maximum? Yes?
An overflow?
Yes, exactly. We have overflow. So overflow, it means that the exponent is too large, and the exponent cannot fit in the exponent field. Remember that this is the largest exponent for single precision and for double precision. This is the largest exponent that you can have in a floating point number. So if you have a number which has a larger exponent, then in this case we say that we have overflow. So that's the meaning of overflow. The number becomes too large. Right. How about the smallest normalized floating point number? Here I mean by smallest in absolute value. I don't mean negative. I mean in absolute value. So what is the smallest in absolute value for normalized? What should be the exponent? Well, 0, it will be, I'll talk about 0 in a minute. Yes, 0 is, okay, has a special representation, but it cannot be normalized. No, normalized, remember that normalized has to have a 1 before the binary point. That's the meaning of normalized. And therefore, 0 cannot be, sorry, 0 cannot be represented as normalized. So it has to have the smallest exponent, okay, for normalized. What's the smallest exponent for normalized? The exponent field. Mm-hmm.
1.
One minus
yes, 1, because 0 is reserved. So we start from 1. This will be the biased exponent, yes. And the fraction field will be what? The fraction.
Zeros.
Yes, thank you. Yes. So if you would like to look at binary representation, the exponent field is 1. Okay, that's the smallest normalized. Okay, because 0 cannot be represented as normalized. This is why we have a special representation for 0. Okay, so I'll come back to 0. So this is the smallest normalized float, and notice that the fraction is all zeros. Now, because it is normalized, there is a 1 and a dot before the fraction. Now we can say, okay, what's the decimal value of this number? Now here, if you would like to look at the exponent value, okay, it will be E, which is 1. Notice that here E is 1, minus the bias, which is 127 for single precision. So now the exponent here is, the exponent value is negative 126, okay, for this number. So that's a very, so the exponent is negative. It's represented as 1, but it is negative, okay? So, so we say that the value is 1 dot the fraction multiplied by 2 to the power negative 100. So that's significant. The significant is 1 dot the fraction, and the fraction is all zeros. So therefore, the significant is just equal to 1. Multiplied by 2 to the power negative 126, you get this number. Now notice that this number is 10 to the power negative 38. That's a very tiny number, very close to 0, but it's not 0. Okay, 0 can never be normalized because 0 does not have any 1 in it, okay, in binary. So therefore, it cannot be normalized. So this is the smallest normalized floating point number. So it's a very tiny number, which is very close to 0, but it's not 0. Okay. We can do the same exercise, okay, for double precision. So for double precision, again, we have the exponent field is 1, and all the bits of the fraction are all zeros. And if you would like to look at its decimal value, now remember that the bias for double precision is 1023. Okay, so you have to say 1 minus 1023, it will be negative 1022. So it's 1.0 because the fraction is 0. So it's exactly equal to 1. That's the exact value multiplied by 2 to the power negative 1022. If you calculate this with the calculator, you get this number times 10 to the power negative 308. This is even a smaller number. Okay, so notice that when you have 10 to the power a negative exponent, it means that this number is a fraction. And this fraction is so small. Yeah, it will be 0. You have so many zeros. In fact, you will have 307 zeros before you reach this 2. So you have to move this dot here to the left so many places, okay? 308 places, and you put a 0. So you have 0.000, so many zeros. 307 zeros followed by a 2. Okay, then we have actually these digits. So before you get the first digit here, you have to have leading zeros in this number. So this number is so tiny, okay, so small, okay, this is why it's represented with a negative exponent, okay? That's the smallest normalized float. Now it's so close to 0, but it's not 0, okay? It's not 0. So that's the smallest normalized float in absolute value. So now you have the range, okay? Now you can say, okay, what's the range of floating point numbers that you can represent? You start at the smallest normalized and you go to the maximum, okay, the largest normalized that we have seen in the previous slide, okay? So you can do it for single precision and you can do it for double precision. Of course, double precision will give you a wider range of values. You can see that the exponent range is large. Okay. Now, the question is, what if I have a number which is not 0, but smaller than the smallest normalized floating point number that can be represented? What will happen? Let me repeat my question. What if you have a fraction, a very tiny fraction, very close to 0, smaller than the smallest normalized floating point number that can be represented? What do you think will happen?
Underflow.
Underflow, yes, thank you. Have you heard about the word underflow before? This is something which is related to floating point numbers. So in the case of floating point numbers, in addition to overflow, it means that the number is too large. It cannot be represented. Its exponent cannot be stored inside the exponent field. You can also have underflow. So underflow exists for floating point numbers. It means that the exponent is too small, okay? It is too small to fit in the exponent field. So notice that here in the case of single precision, you can go to negative, negative 126. Okay, this is the base, which is 2, because everything is in binary, but we have converted it to decimal. But in binary, okay, it's negative 126, but we add to it the bias, which is 127, and we represent it as 1. In the case of double precision, you can see that the exponent is negative 1022, but we add to it the bias, which is 1023, and we store it as 1 inside the exponent field. Okay, so if you have an exponent which is smaller than the smallest exponent that can be represented, then in this case we have underflow. So the exponent is too small and it cannot fit in the exponent field. That's the meaning of underflow. So the number is so tiny, okay, it's very close to 0. Now in this case we can approximate it as 0. Okay, we can approximate it as 0. So let me talk about now 0, infinity, and not a number. So what we have seen so far, we have seen normalized floating point numbers. But this is not sufficient. Okay, it's not sufficient to represent all numbers. We should be able to have a special representation for 0. Now 0 cannot be normalized. Okay, it cannot be normalized. And therefore, there is a unique representation for 0. Now, the exponent field must be 0. This is why I said that we cannot use the exponent field equal to 0 for normalized, because it is reserved for the number 0. So the exponent field is 0 and the fraction equal to 0. So basically, all the bits of the floating point number are zeros. All the bits are zeros. And this is the number 0. Now, because we have a sign, we have a special bit, which is the sign bit, we can have +0 and -0. That's okay. This is allowed in the case of floating point numbers. You can actually have +0 and -0. So in the case of 0, we ignore the sign bit and we just say that the number is 0. Okay. So these both are possible according to the sign bit. Okay, so both are possible. And we say that +0 is equal to -0, and we simply ignore the sign bit. Clear? So this is the representation for 0. Okay, so we have seen in the previous slide that for normalized, we cannot use the exponent field to be 0. But now, in the case of 0, I will have to have the exponent field equal to 0. So the number is no longer normalized, and it represents the exact value of 0. There is a representation for infinity. Now, infinity here is a special value in the case of floating point numbers. Now, we have this infinity in the case when we have overflow. If the number becomes too large and it cannot be represented, then in this case, we say that the value is infinity. Okay, so we say that the number is too large. And for example, in the case of overflow, we can say that the number is infinity. Or when we have division by 0, when we divide by 0, then the number becomes, so the result is infinity. And for example, 1/0, okay, the result will go to infinity. So this is the meaning of infinity. So it has a special representation. We use the maximum E. So the maximum E here means that all the bits of E will be ones in binary. If you look here at the exponent field and all the bits are ones and the fraction is equal to 0, then that's the representation for infinity. So in the case of single precision, maximum E is equal to 255 because we only have 8 bits. Okay, so we don't use this number to represent normalized floating point numbers. We use it to represent infinity. Okay, and we make sure that the fraction is equal to 0. In the case of double precision, because we have 11 bits, then the maximum exponent will be 2047. So remember that in my last lecture, I said that these values are reserved. Okay, so we don't even use the maximum value of E because I'm reserving them for the infinity, and also there is another special value which is not a number that I will talk about it in a minute. Okay, now infinity can be the result of overflow or division by 0. So it means that this number is too large, it cannot be represented. And because we have a sign that, then we have two possible signs for infinity. We can have plus infinity and we can have negative infinity, and both are possible according to the sign bit S. Okay, is this clear? So this is a special value that we can have. Yes, Amr?
Yes, Victor, I have a question about the 0. Why we need the E to be 0 also? Is it enough for F to be 0? Then we can say we have 0.
No, because you see that if the fraction equal to 0 and E is different from 0, then the number is normalized. Okay, and if the number is normalized, you will have a 1 and a dot before the fraction, and the fraction is no longer, so the significant is no longer 0. Yes, the fraction will be 0, but the significant will be 1.0. That's in the case of the, remember that in the case of the smallest normalized that we have seen in the previous slide, we had the fraction equal to 0, and we had the exponent different from 0, and this gives me a number which is different from 0. It gave me a normalized floating point number.
Okay, thank you. I forgot about the 1.
Yes. So there is always a 1 and a dot before the fraction if the number is normalized. So for 0, we had to have the exponent field equal to 0 to indicate that the number is not normalized. Okay, and it is used to represent the special value 0. Now there is another special value which is called not in number, nan, not in number. Now nan is a special value, okay, which is interesting in floating point numbers. Now this nan, okay, is represented with the maximum e. So we use the same maximum e which is used by infinity, but we make the fraction different from 0. Okay, usually there are special values for the fraction that indicates that the number, so if the fraction is not equal to 0, then we say that the number is, the value is nan. Okay, it's not in number. Okay, it's special value, and it's not infinity, it is nan. So if the fraction equal to 0, so if you have the maximum e and the fraction equal to 0, then the special value is infinity. If we have the maximum e and you have the fraction is not equal to 0, then the special value is nan. Now, for example, we can use nan for certain operations. Yani, for example, if you are dividing 0 by 0, then the result is undefined. So we say that it is nan. Or I multiply 0 by infinity, I say that the result is nan. If you take the square root of a -1, then the result is not a real number, it's an imaginary number. So therefore, we say that the result is nan. It means that the operation is invalid. You have an invalid operation. Okay, so this is why we say that the result here is invalid. And to say that the result is invalid, we say that it has a special representation, which is called nan. Now, if you take a nan and you add it, let us say, to any number x, you get nan. If you multiply it with a number x, you get also nan. So if you take any operation and you have one of the operands here is a nan, so you would like to operate on two numbers. One is x, x is a valid, let us say, a normalized floating point number. And the second one is nan, you get nan, okay? So there are rules, okay, for producing these special values in the IEEE standard. So that's the meaning of nan. Now there is one more. There is one more concept which is used in the IEEE standard, which are denormalized floating point numbers. So far we have seen 0, we have seen infinity, and we have seen nan. Let me talk about denormalized floating point numbers. So far we have seen normalized. Normalized means that you have the range from 2 to the power for single precision. You can go from the smallest normalized, which is 2 to the power -126, to approximately 2 to the power 128. Slightly less because we approximated this as 2 to the power 128. That was the largest normalized that we can represent. This is the range, okay, of normalized floating point numbers that can be represented. So you have a range for positive normalized. We also have a range for negative normalized according to the sign bit. So we have these two ranges of normalized floating point numbers. Now, if you have a number which is greater than the maximum normalized, then we have overflow. You can have overflow in the positive direction. You can also have overflow in the negative direction. So we call it positive overflow, and we can call it negative overflow. So the exponent becomes too large and it's represented by all ones. Okay, that's an indication, and the fraction field is equal to 0. That's an indication of overflow. Now that's the meaning of overflow. In the case of underflow, if the number becomes smaller than the smallest normalized floating point number, okay, then we have underflow. So the meaning of underflow, it means that the number is so tiny, it's so close to 0, but it's not equal to 0. Now remember that we have a special representation for 0 in the case of floating point numbers. The exponent must be equal to 0 in binary, and the fraction must be also equal to 0. So between the smallest normalized and 0, we have numbers, and these numbers are called denormalized numbers. So we can have underflow. And underflow, it means that the exponent is smaller than the smallest normalized exponent. So in the case of denormalized, we replace the 1 and the dot that appears before the fraction. This is replaced by 0 dot. So we say that the number is denormalized. And these are here. So we write for single precision. Okay, so if the exponent equals to 0, so the exponent field must be 0. The fraction field can be anything, and the sign bit can be anything. So according to the sign bit, we can say plus or minus according to the sign bit. Now we write the significant as 0.f because the number is denormalized. Okay, it's no longer normalized. So we have a 0 and the dot before the fraction, and we use the smallest exponent, which is negative 126 for single precision, or negative 1022 for double precision. So these are the denormalized floating point numbers for single precision and for double precision. Now notice that these numbers, because the fraction here can be anything, okay, then these numbers are smaller than the smallest normalized. So these are very tiny numbers. According to the fraction field, you can represent many numbers. Yani, for example, if we are using 23 bits of fraction, we can have 2 to the power 23 possible fractions here. Okay, and these can represent values which are smaller than the smallest normalized. The smallest normalized is 1.0 times 2 to the power 126. This is 0 point something. So this is smaller than the smallest normalized, and this is why we call them denormalized, and these are very tiny numbers which are very close to 0. Now we call it gradual underflow. The meaning of gradual underflow to 0 is that when the fraction becomes 0, we got 0.0 times 2 to the power negative 126. So we get exactly the number 0. So when the exponent is 0 and the fraction is also 0, we get the exact number 0. So denormalized, it means that the exponent is 0. Okay, the exponent field is 0, but the fraction is different from 0. And when the fraction becomes 0, then we get the exact number 0. That's the representation for 0. Is this clear? So we can have denormalized, which are positive or negative according to the sign bit. They are both called denormalized, and this is just a small range of very tiny numbers which are not normalized. So we call them denormalized. Okay? So in summary, we have seen the IEEE 754 standard. This is how the IEEE 754 standard defines floating point numbers. So in the case of single precision, we have 1 bit for the sign, we have 8 bits here, 8 bits for the exponent, and we have 23 bits for the fraction. Now, if the exponent field is from 1 to 254, we use it to represent normalized floating point numbers. And the fraction can be anything. And we say that the value is 1.f. 1.f is the significant. So the 1 and the dot are implicit. So we say that 1.f multiplied by 2 to the power e minus the 127. Remember that 127 is the bias. And the sign can be anything plus or minus. So this is the meaning of normalized. Now, if the exponent field is 0 and the fraction is not 0, we call it denormalized floating point number. And we replace the 1 and the dot with a 0 dot. So these are implicit. They don't appear in the number. And we use a fixed exponent, which is negative 126. Okay, that was the smallest exponent for normalized, and we use it for denormalized. So all the denormalized floating point numbers have an absolute value which is smaller than the smallest normalized. Now, if the fraction becomes 0, if the exponent is 0 and the fraction becomes also 0, then this will be the exact value of 0. Because we have a sign bit, you can have plus or minus 0, but we ignore the sign bit in the case of 0. Infinity is represented by the largest exponent, which is 255, and a 0 fraction. Now, here the sign bit is important, so we can say plus or minus infinity. And this can be the result of overflow, or it can be the result of division by 0. Okay. And finally, we have, so this is the meaning of infinity. Finally, in the case of not in number, this is a special value. So the exponent is 255. That's the largest exponent. So all the 8 bits are all ones in binary. And we have a non-zero fraction. Okay, in this case, we say that the value is not in number. So for example, when you are dividing 0 by 0, or multiplying 0 by infinity, or you are taking the square root of a negative number, then in this case, we say that the value is undefined. Okay, and therefore we say that the value is not in number. It's not a real number, or it is not determinate. It's not defined. Okay, like for example, 0 divided by 0 is not defined in mathematics. So we say that the result is none. Okay, not in number. Any question about this? Notice that exactly the same concepts apply for double precision, but for double precision, we have the exponent field is equal to 11, and the fraction field is so 11 bits for the exponent, 52 bits for the fraction, and the bias is 1023. And for denormalized, we use actually a fixed exponent, which is negative 1022. It's exactly the same concepts which are also replicated for double precision. The difference is that we have a wider range of exponents in the case of double precision because we are using a bigger exponent field, and we also have more bits in the fraction, allowing more precision, more digits, okay, appearing after the decimal point. Okay, when we convert the number from binary to decimal, you can actually get more significant digits, okay, in the floating point number.